Professor Hanqing Jin from Cambridge. He's going to talk about, from Oxford. I always mix up with the two universities. And he's going to talk about adaptive partitioning and learning for stochastic control for diffusion process. Thank you.
Firstly, thank the organizer for the invitation. And for the extra time, of course, not from the organizer, but for some unfortunate reasons. Right? Anyway, I will still try to finish as quick as I can. So this is a joint work with Ren Yuan and my PhD student Yan Zhao Yang. Okay, so this talk stays in almost the same big framework as the previous talk by Yuxin Chen. So, well, he gave a very good explanation of the whole framework. So it will save me a lot of explaining my big ideas. Okay. So let me start from our real problem behind this work. So this is motivated by portfolio selection in finance. So we will stay in a discrete time system. Okay. Of course, in finance, portfolio selection, most portfolio selections were studied in a continuous time setting. But here we think we are doing the problem after some discretization in time. So we will stay in a finite discrete time system with some state process X. Okay. So we set our state space to be the whole real space. Okay, real vector space, and the action space. Typically, in our applications, the action space should be unbounded, or maybe, for example, also in some d-dimensional, multi-dimensional real space. But we still don't have. We didn't start to study that case, so we focus on a problem with bounded action space, but continuous. Okay. So the dynamics of our state process is given by this diffusion, the discrete time diffusion. By this one, where this mu h, sigma h are some function, but we don't know. Okay, and starting from some initial states which follow some given distribution. Here, BH is a representative of discretized Brownian motion, and well, multidimensional. This delta is the time difference in one step, and AH is the action. Okay. In the action space, that's it. And our optimization will be over the control A, and here we use the reinforcement learning framework to say our policy is a distribution over the action space. Okay, and because of this Markovian property of the system, we only consider the distribution which depends only on the current state of the system. And the objective, or the reward function, is to maximize the expectation of the accumulated reward, where each reward is a random variable following a given distribution determined by the current state and the current action. Okay, and this action is a random variable which will be decided by its distribution will be decided by the policy pi. Okay, now of course we need some regularity of the system So if we denote this little rh as the expectation of our instant rewards, okay, given the current state and action, then we need our expected reward to satisfy this continuity. This is we call it as polynomial growth condition. Okay, where this m is some positive number, and anything else? And furthermore, we also need the randomness behind the reward, the instant reward, to be regular enough. So we use this sub-Gaussian property. Okay, so there exists some theta to control the diversification of this distribution. Okay. And for our system, the mu sigma drift and diffusion function, we also need them to be regular enough. Here we impose the Lipschitz linear growth conditions. In fact, in our discretized system, we can make it more relaxed. Okay, but because, as I said, the motivation was from portfolio selection in continuous in financial markets, where the dynamics comes from a stochastic Fisher equations. Typically, those mu sigma are assumed to be Lipschitz. Okay, so this is from our motivation, not from what we need here. Okay. Furthermore, we assume our initial distribution of the states has some finite moment to some order. Okay, we use this no. Okay, we assume it has a finite piece order moment. Okay, for some p big enough, at least the p need to be bigger than m+1. Otherwise, the objective may go to infinity. Okay, and the system must be okay. The drift, the diffusion must provide some information to learn. So we assume this sigma, the diffusion coefficient, is positive enough away from zero. Okay, so this condition in our analysis is quite necessary, but in our real application, in our numerical experiments, we find if our sigma does not satisfy this condition, our algorithm still works quite well. Okay, so well, we don't want to get into more difficult in analysis in what will happen if we don't have this lower bound of this sigma. But okay, we'll see. So this is the standard notations in the reinforcement learning for the control problem. Okay, so we studied the value function, Q function, and the optimal ones we denote by V star, Q star. Okay, these are all introduced in the previous talk by Yuxin Chen. Okay, so with our regularity I showed in the previous page, we have this estimation of the regularity of our value function and the state process. For example, we can find a constant MP such that the whole state process, okay, over the finite time horizon, will stay in a big ball with high probability. It's this one. Okay. In fact, this MP is the piece order moment of the initial distribution. Okay. And the value function is polynomial dominated. okay, with some constant C tilde. And the value function is also locally Lipschitz with this x to the power m coefficient. Okay. Okay. Now, well, very different from what was introduced in the previous talk by Yuxin Chen. Here, our state space and state space and action space are both continuous, and our state space is unbounded. So we need to do the partition to take advantage of the reinforcement learning algorithms. So, for example, an easy partition is just to even partition the big space, but of course this will be very, very costly. Okay, and both in terms of space and time. So here we try to use smarter partitions called adaptive partition. So the idea is, okay, we don't do the partition for all in the whole space, but we only do some partition over those regions where we visit often, or the more often we will make our partition final. Okay, when time goes on, we will get we will collect the information how often a region will be visited. Okay, so this is the main idea to for this adaptive partition. So we will do this way. So at each time step, okay, we will keep a partition of the space, the state and action space, starting from a very close one, okay, and then we will run the system, and we will count the visitation counts for each blocks in our partition. Okay, but this visitation count is not just the accurate one, well, how many times our state process visited this block, but we need also to collect the information of its ancestors. Okay, because we are partitioning the blocks fine and fine. So well, we need more information to do some estimation of our Q function or value functions. So this I use NKHB to make the visitation counts of a block and its ancestors. Okay, H means the time, K means the episodes. Okay, so when NHK, when this visitation count is big enough, it will trigger the splitting of our current block. Okay, so for the splitting, we can just split it into half size of sub blocks. Okay, so it depends on the dimension of the space, right? So if dimension of space, state space is ds, action space is dA. So each splitting will split the block into 2 to the power of 2 ds plus dA small blocks. Okay. So we will try to control this splitting by a so-called confidence criteria function, okay, which will be a function of the visitation counts only. It's a decreasing function, and it should vanish when the visitation counts goes to infinity. We will determine this confidence criteria later. Okay, so this is a typical snapshot of the adaptive partition. So you see here, the first B1 means B1, B2 is the starting partition. We partition the space into 2, and when time goes on, we can see the color means some represents the frequency of the visitation. Okay, so the more frequency an area is visited, and the finer our partition will be. Okay. Okay, here the main difficulty we saw comes from the unbounded state space here. Well, if the state space is unbounded, then we will have, for example, if we do the even partition, then we will have infinitely many blocks. It's impossible to record all those behaviors over those blocks, right? So, well, even in the adaptive partition, this unbounded space make quite a lot of troubles. So here, our idea to tackle it is at the beginning, we need to choose a big ball, and we will only do this adaptive partition over this big ball. And for those states going out of this big ball, we ignore it. And we deal with that case by the probability that the state space will go out of the ball with a very, very low probability. Okay, and hence later we will try to balance the final performance by choosing proper size of this ball. It's called a rho. Okay, so you see why I give a estimation of the probability that the state process goes out of the big ball. Okay. Yes. Now another difficulty is the polynomial growth of the rewards. Okay. Because this polynomial growth only gives us a locally Lipschitz property. And this will make our estimation and error bounds of Q functions much more complicated than the case with uniform Lipschitz conditions. Okay. We will see it later on the detailed calculation. Okay. So let me try to explain what we will do in each episode in the episodic calculation. So in each episode, episode K, we can with some initial states x1. I denote by K because the initial state just follows a distribution, and we will run the system according to the control system according to some estimation of the Q function from previous episode. I denote by QK minus 1 H. Okay. So at yeah.
Sorry, I lost track. B is contains both the state and the action, right?
Yes.
Yeah.
Yes. Yes. So we will split. We will partition the product space. Yeah. Yeah. That's very critical because later, this block will also imply the information of our action. So in each episode, we will start from time 0 or time 1, and we will run the control system to the end of the time horizon, and in which we need to decide our action or our control. Right? So the control can be decided by the estimation of the Q function from the previous episode. So here we use the greedy selection, okay? Because here now we partition the whole space into blocks, so the optimization will be over blocks. Like for each time h, we can observe the current state xhk, and then decide, and then we can find a set of a family of blocks which contains this current state, and then we will try to maximize the previous estimation of Q function over all those blocks. And we, for example, we use this BHK to denote the maximum one of this Q function. Okay. Well, in case there are multiple maximum blocks, we just randomly pick up one from it. Okay, and then we need to decide the action, right? The accurate action to run the system. So we take an action A, HK uniformly from the block of the state, the action space in this BHK. Okay, and run the system to get the instant reward and the next state HK plus 1, and then we can update the visitation counts by increase by 1 of the specific block, and of course copy the other visitation counts for other blocks. Yes, and then we need to do the splitting if a split is triggered by the confidence criterion. Okay, and well, by the way, here I said if we need to choose B to contain this XHK, right? But in case that XHK goes out of the big ball we drew, then we don't need to do anything. We just pick up a fixed action for that state, and we don't do any updates of the estimation of the counts of visitation, because well, this is because the probability of this happen is very low, so we don't care. So I mentioned this just want to make our algorithm complete. Okay, finally we need to update our estimation of the Q function and value functions. Yeah. So now the critical thing is the estimation of Q function. Okay. So recall that Q function consists of two parts. One is the expected instant reward, and the other is the value function from the next step. So we estimated these two parts separately. For the first part, is expected the instant reward. So the information we collected are those visiting of the current block and its ancestors. So we collect all this information up, and we just use the sample mean. The sample mean to estimate this expectation. Okay. Well, it sounds like the error can be quite big, because here the visitation may not be that much, right? And this is a block. It's not the block may come from a very big one to some small one. So the error can be quite big. But fortunately we have this upper confidence bound, something like that. So given any small probability delta, okay, and we can have at least probability 1 minus delta, such that for any episode, any time step h, and any block with strictly positive visitation counts, we have our error of this estimation is bounded by these two terms. Well, the first term is, well, you don't need to look at all terms, but this visitation counts is an infinitesimal of the order of n HKB to minus half. Right? And the other bit, the R bias term, is something linear to the diameter of this block. Okay, so so this is quite good. So we can, so in the future we need to balance these two parts of error in our estimation. Now, the other bit is the expectation of our future values, and for this estimation, we need to estimate the transition probability, right? And fortunately, in our case, because of this diffusion model driven by Brownian motion, we have the normal distribution. So this estimation can be done by the estimation of this mu drift and the volatility. Okay, so our estimation is quite standard. It's just the standard sample mean, something like sample variance. Okay, of course this is a matrix, variance covariance matrix, and then this estimation of this transition kernel is just the normal one with the estimated mean and variance. Okay, it's quite well. At the beginning, I don't really believe this can work, but it works. Okay, so well, with this estimation of transition kernel, we naturally estimated this second part by the expectation of our future value with the random variable xk plus something like xhkh plus 1 follow the estimated distribution, and the value function, we can only use the estimation of the value function from the previous episode. Okay, so yes. Now we need to find some upper bound of this error. So we have this. We have this. Okay. We have this upper bound. Again, it consists of two parts. Okay, the first part, TUCB, is much more complicated than the previous one, but it is a infinitesimal of nh1 over n square root nhkb. Okay, and the second bit, the bias term are the bias part is some constant or some function of the current state. So this x to the circle B is the center of the state in this the current block B. Okay, so it's a function of the size, the position of the current state times the diameter of the current block. Okay, now with this estimation of those error bounds, we can construct our estimation or update of our Q function and hence the value function by this formula. So Q is estimated by its estimation R hat and its error bound RUCB plus some term. Okay, the bias term will be combined into this total bias term, and the expectation of a future value function will be estimated by this one and plus its error bounds Tucobi and other bias. So the two bias term will combine together. Okay, but remember, both of these two terms will be infinitesimal of 1 over square root of visitation counts. So this is the updating for all blocks in our big ball. And if the state goes out of big balls, then we just use a common upper bound, starting from starting from the big ball. So we just pull the state x to the boundary of the ball and add some extra term according to some local Lipschitz condition on the value function. Okay. Well, anyway, this does not really matter because we will finally control it by the probability. Okay. Now the confidence the confidence criteria for the splitting can be used to control to balance these two terms, two terms of the error. Okay. The first two is in the order of visitation count to the minus half. And this bias term is a linear term, something like a linear term of the diameter of the block. So to balance them, we could design our confidence criteria as a polynomial function of the position of the block and the square root of the visitation count. Okay. Well, at the beginning, we think we can do it starting from the most close partition, that is the whole space. Well, and of course, with the intersection of the big ball of the state space. But it turns out that it's quite nasty to do the analysis. We can't control some coefficients in front of the estimation of the error. So we start with some finer initial partition. Say, okay, firstly, we partition the state space into hypercubes with a fixed size. I denote by d hat. And then we start with the partition of the big ball by pick up all those blocks, the big blocks in the state space times the whole action space. Okay? Well, our action space is finite. And all those blocks are in S. Well, I call the big ball as S1. All blocks in S1 is also finite. So we have finite blocks in the initial partition. We also need to set up the initialization of our estimation of Q function and the value functions. And this is quite straightforward. It's that, the initial estimation must be a upper bound, must be bigger than the real value function, the Q function, right? So we simply pick up some upper bound we estimated at the beginning of those value functions. Like Q bar is this one, V bar is this one. Well, because here we have the polynomial dominance property of the value functions. So this is quite easy to get. But interesting is here we also need some other functions to pass information from the estimation of a Q function to the value function. Okay, but remember we needed the value functions from the previous step to continue the estimation of our Q function. Okay, so this is some detailed construction of our learning on the value functions and the Q functions. Okay. So with this initialization of the value functions and the updated rule in the last page, we can prove that, roughly speaking, our estimation of the value function is bigger than the real value function with high probability. In the sense that for any small probability delta, we can have at least 1 minus 3 delta probability that this estimation is bigger than the real value function for all hk and all x. Okay. And this is our algorithm. Well, I just now explained the idea of the algorithm. Yes?
So, can you go back to the last slide? So you're saying you're overestimating the value.
Yes. Yes.
So, how about, so why is that a useful criteria?
Good question. So later, because we will do the regret analysis, we need to evaluate V star minus our V pi, right? But we don't know V star. So we will replace this analysis by starting from V bar minus V pi, okay? And if we don't have this this comparison, we don't know the property of the real regret, right? But with this property, we just make our estimation of regrets bigger. Yeah. Ideally, this V bar, this V bar should go decreasingly to V star. But well, here we roughly we have the sense that it should go decreasingly, but not really. Even with high probability, it may sometimes or at some place it may go up a little bit and then go down. Okay, so this is the algorithm. Well, I don't need to read all those steps, but the idea is there. And now we need to do the convergence analysis. We do it by this the regret analysis. So this notation was already introduced in the last talk. I don't need to repeat it. Okay, so we denote the pi hat as the policy we obtained from our algorithm. And then we have this big this main result, which says if our initial distribution is good enough, that is to say, this P satisfies this condition. It's not. It's quite mild. It's not that strong, and then we can take the size of our big ball, this rho, to be the size of a big ball to be k to some power beta. This beta is definitely smaller than 1. Well, as this. This monster comes from our calculation. We can't simplify it, but so we just keep it there. Then for any small probability delta, we can ensure with probability at least one minus 6 sigma that our regret is bounded by this this order. I say this order. We have several terms. Well, I make it this many terms because I also want to emphasize the role of h, the number of time steps there. Okay. Of course, here our analysis focuses on the order of the episode, the k. Okay. So the k, roughly speaking, here the leading term is this one. Well, this C1, C2, these three, these constants can all be calculated explicitly. Okay, well, because it's quite complicated, I don't want to show it. So the leading order is this k to the power gamma plus times log k to some power. Okay, this gamma is this one. Okay, it's not that interesting to look into the details. Oh, sorry, I forgot to mention this Z max C. Z max C is the so-called zooming dimension of the, well, it's a property of the near optimal set. Okay, roughly speaking, so how close our action or our control is close to the no, it's not how close, it's set that's our that's around the optimal control where we are. Okay, so this leading order, well, sometimes we call the order is gamma, right? Gamma is this one. Looks quite complicated, but well, we are more interested in the asymptotic order by saying when p goes to infinity. Okay, p goes to infinity is something like the initial distribution has infinite bounded infinite order moment. Sorry, for example, if the distribution is Gaussian, or is with compact support, then this p can be any big number, right? So the asymptotic order, this gamma is something like this one, and this zooming dimension is bounded by the sum of the dimension of state space and action space, so ds plus dA. Okay, so this is a quite good number. Okay, now let me show you by a very simple example of well, it comes from the mean variance portfolio selection. Okay, so the mean variance portfolio selection is quite standard. The mean variance is a quite standard one. We invested in a financial market with a risk-free asset and two risky assets with independent random source. Yes, and the portfolio. Well, we use the so-called proportional portfolio. That's this A1, A2 represents the proportion of total wealth in the two risky assets. Okay, and we don't allow short selling, and we don't allow borrowing. So this action, this portfolio stay in simplex. Okay, that's it. And the wealth is the state's process of the system. The dynamics is given as this one. It's clearly satisfies all properties. Well, all properties of what we have, other than the property that sigma. Remember the coefficient of the diffusion. Our sigma must be strictly positive definite. Here we have a little bit trouble on that condition. But as I said, our final performance of the numerical results still quite well, even we don't have this this lower bound. Yes, and the rewards. Here we assume all rewards are deterministic. There's no randomness. So the distribution of the rewards are single points. Okay, and we don't, well, mean variance, we don't have intermediate rewards. All rewards come from the terminal values. So for h less than capital H, it is just a 0, and at terminal time is a controlling function of the state. And this nu is a constant which will be determined by the mean variance, the trade-off between mean and variance. Okay, so we did the experiments by setting some parameters like this way, but it doesn't matter. What matters is the number of episodes. We tried 1,000, and this row should be in the order of k to the power some beta. Determined in our main theorem. This is the performance. So the horizontal axis is the number of episodes, and this vertical axis means the total observed reward of course, here, or total observed reward is just a reward at the end, right? So we get this kind of performance. So you can see, starting from something like 300 or so, the performance quite stable. So the convergence quite quick, quite stable. And from the stable states, there's something like this is the performance. It involves some variance. So you can also see that the variance of the objective is also quite small. Okay, and finally, this is the a study on this convergence order. So we take the log points of our experiments, and we see and we do this linear regression, and we find this log slope is about 0.52. So this should be the order of regret with respect to k, right? And this is better than what we have expected. Okay, so in our case, we start from a fixed point of the initial state. Hence, p can go to any number, go to infinity, and we can talk about the asymptotic order. In this case, this is the asymptotic order is this one, and this z is the zooming dimension. I mentioned this zooming dimension is less than ds plus dA, and now we get the sense how big, how smaller it is. Okay, so ds plus dA. Use ds plus dA to determine the asymptotic order. It should be 0.8. Now we get 0.52. Okay, it's a big difference. It's not just a difference of 0.2 something. Okay, because this is the difference in order. Yeah.
So the graph here, the gamma, the pony is decreasing as the next step. So the gamma here is decreasing as the dimension increases?
It's increasing. So when, for example, when ds or the dimension goes to infinity, this converges to what?
Right. But then the record, I remember, is 1 minus, or which is
No, 1 minus is in the definition of gamma.
okay.
Can I show you? It's 1 minus these things. Yeah. Okay, I think I'm done. Time is up. Okay, I'll stop here. Thank you.
Questions?
Yeah.
So you've shown results for simulation with 2 dimensions. How many dimensions does this?
Well, the state space is 1 dimension in our example. It's the total Wells process. Yes, and the second, the 2-dimension this is the market. Yeah.
But in practice, how many dimensions can I do?
Well, because we didn't use the supercomputers, so we just try a little bit in 1 dimension. But the dimension is really a big problem. So here, we believe we can release the curse of dimension quite significant by this adaptive partition. But we don't know how much we can reduce. Definitely we can.
Questions? I have one question.
Yeah.
So for the partition, looks like you're doing the box partitions.
Yes.
First question, have you thinking some other partitions like triangle as a shape? And secondly is, so this is one way doing the partition, I was thinking about someone saying there's the blocks here on the PDE. One is a partition, the other one probably can think about some embedding for the global dimensions. And the whole purpose is trying to make sure this thing is computable. So one is a partition, the other way you can probably just put in some neural net as the embedding, and then hopefully for the embedding latent space, then you go ahead to pick out the action.
Okay.
Questions.
Yeah. Well, for the first question, the focus. Sorry.
Yeah, the partition. Why stick to those things?
Yeah. It's a very good question. So in fact, in our application, the real action space is not a hypercube. It's something like a triangle, right? I think it may be better to use some other shape of the blocks, especially in action space. But here we do this hypercube just for the convenience of analysis, right? Sometimes we even had thought about to use balls, but well, the partition by balls is not really good. You can't do the real partition. There will be many overlaps. Yeah. Yes, that's true. I think in practice we should use different shapes of blocks. Yes. For the second one, we have not tried to think about it. The reason is if we use, well, in my personal understanding, if we use something like a neural network or other way to embed the space into some lower dimensional one, I think that, well, at least it will introduce more errors into our calculation. At the current stage, we are quite happy with what we obtained. This something like error bound, but I don't know how to do the estimation of this convergence with extra reduction of the calculation.
One question. So you mentioned this you have this uniform electricity assumption, but this problem you presented, can't you just look at the log valve and then it would actually be satisfied already?
Yes, but other conditions will be broken.
Ah, I see. Okay, thank you.
Yeah.
Okay, thanks speaker again, and lunch.